In this lesson, we use a very popular rule called the chain rule to differentiate a composite function. Here's what the chain rule says. If f of u is differentiable at the point u, which is equal to g of x, and g of x is differentiable at x, then the composite function f composed with g at x, which is defined to be f of g of x, is also differentiable at x. So it's very important that we understand that f here is our outer function and g is our inner function, okay? F is our outer function, g is our inner function. And so then the derivative of this composite function is equal to the derivative of f, which is the derivative of your outer function evaluated at your inner function. So f prime of g of x times g prime of x. So this is a derivative of your outer function evaluated at your inner function times the derivative of your inner function. For example, look at this function. Y is equal to 3x squared plus 1 quantity squared. Now this for sure is a composite function. I'm going to move the board up just a little bit here. I'll still display the chain rule up top, but I just want some space. All right, so this for sure is a composite function because we can say let our outer function, I'm going to call our outer function f, okay? Our outer function can be x squared, and our inner function can be 3x squared plus 1. Now, this for sure gives us y because this is the number 3 right here, folks. Don't want to confuse anybody, so let me rewrite that. Number 3. Okay, very good. This outer function and this inner function, when composed together, gives us y. And I can show that, f composed with g at x is defined to be f of g of x by definition, which is equal to f of 3x squared plus 1. That's what g is. And then this notation says to evaluate f at the expression 3x squared plus 1. F is just squaring your input. So then this would be 3x squared plus 1 quantity squared, which is exactly what they're saying y is. So all I'm trying to show here is that y is indeed a composite function. All right, so we're going to use the chain rule to find the derivative of y. Okay, here we go. So y prime, I can write that as dy dx, but I'll just write y prime is equal to, I'm going to write this down here, okay? It will be equal to f prime evaluated at g of x times g prime of x. This is the chain rule. So then it is, let me move this up now. The f prime right here represents the derivative of our outer function. The derivative of the outer function is 2x. Okay, so it's 2 times, now be careful here, the derivative of your outer function evaluated at your inner function. So it's 2 times, instead of it being x, it's 2 times 3x squared plus 1. There, right? So it's the derivative of your outer function. So it's by the power rule, this is 2 times x. But 2 times x, that represents 2 times this input here, okay? Times the derivative of g, all right? And the derivative of g is 6x. So this is times 6x. I hope that makes sense for you. So then y prime is equal to 12x times 3x squared plus 1, which can be simplified as 36x cubed plus 12x. All right? So once again, it's the derivative of the outer function evaluated at the inner function. All right? So this is 2, the derivative of x squared is 2 times x, but when we say x, we mean your input. So it's 2 times this input, right? So 2 times g of x here times the derivative of g of x, which is just 6x. All right, let's do some more examples. I think the more examples we look at, hopefully the more comfortable we feel with using the chain rule. All right, cool. All right, we have a brand new function. We want to differentiate this with respect to x. Now, this is indeed a composite function. If you'd like, I can show how this is a composite function. I can say let the outer function, I always like to call my outer function f, but I will say my outer function is just the sine function, and my inner function, which I'm calling g, is the argument x squared plus x. Just in case, I just want to make sure that everyone sees how that when I compose f and g together, that I get this function that they're giving me. So this is by definition f of g of x. So then this is f of x squared plus x. And so I plug this or substitute this expression into function f, which I'm calling sine. So then it's sine of, and then x squared plus x. So this is indeed, this function here is indeed a composite function, with the outer function being the sine function and the inner function being x squared plus x. So now I will use the chain rule to find the derivative. All right, so here we go. The derivative with respect to x of sine of x squared plus x, okay, is equal to, all right, here we go. The derivative of the outer function, that's cosine of x. But be careful, it's cosine of your inner function, right? This is the derivative of your outer function evaluated at your inner function times the derivative of the inner function. And the derivative of this inner function is 2x plus 1. All right, so this here is the derivative. I do want to rewrite it though. I'm going to put 2x plus 1 in the front. So it's 2x plus 1 times cosine of x squared plus x. I would hate for someone to multiply these two binomials. You cannot do that, right? It's cosine of this argument and then times 2x plus 1. So just be careful there. All right, very good. All right, folks, we want to find the derivative of the following function. G of t is equal to tangent of 5 minus sine of 2t. All right, very good. So there is an outer function, which that is the tangent function, and the inner function is 5 minus sine of 2t. Now, there's a lot going on here, so let's do it. So g prime of t, okay? We're definitely using the chain rule here. The chain rule says to find the derivative of the outer function, and we're calling tangent the outer function. Now, the derivative of tangent is secant squared. So it'll be secant squared of this expression here. So remember, it's the derivative of the outer function evaluated at the inner function. There. Now, times the derivative of this inner function. Now, the derivative of this difference is equivalent to the difference of the derivative. So, times the derivative of 5, which is just 0, minus. Now, it's the derivative of sine of 2t. Now, this in and of itself is the chain rule once again. All right, so here we go. For this, this would be a composite function whose outer function is the sine function, whose inner function is 2t. The derivative of sine is cosine, so it'll be cosine of 2t times the derivative of 2t, which is just 2. If I can fit that, times like that, times 2. All right, very good, very good. So let's see if we can just clean this up a little bit, all right? So secant squared of 5 minus sine of 2t, like that, times negative cosine of 2t times 2. I'm going to close that set of parentheses there because I don't want anybody to multiply 2t and 2 and make 4t. You can't multiply this argument by 2, right? It's cosine of 2t and then times 2. All right, so we can clean this up just because this looks a little messy here. This 2 right here and this negative I'll pull out to the very front. So it'll be negative 2. And then I'll write it as cosine of 2t times secant squared of 5 minus sine of 2t. All right, very good. That's the derivative. We had to use the chain rule here 2 times, right? We had to use the chain rule first because tangent is the outer function and all of this in here is the inner function. And then the inner function in and of itself has the chain rule because, or needs the chain rule because this term here, sine of 2t, is also a composite function. So you kind of have a composite function within a composite function, you know? All right, cool. Let's continue finding derivatives. All right, let's look at a few different expressions and find the derivative, all right? The first one is 5x cubed minus x to the 4th, quantity to the 7th power. Now, this requires the chain rule and the power rule, all right? So let's go for it now. So d dx of 5x cubed minus x to the 4th to the 7th power. Okay, so this is equal to, by the power rule, okay, the 7 comes down, and now 5x cubed minus x to the 4th now is raised to the power of 7 minus 1, which is 6, times the derivative of the inner function, right? So again, this, maybe I should have said this in the very beginning, this can be considered a composite function, where the outer function is x to the 7th power, and the inner function is 5x cubed minus x to the 4th. So the first thing I'm doing is using the chain rule to find the derivative of the outer function, which has me using the power rule to do that. So the 7 comes down, and then this expression is raised to the power of 6. But now we're not done. Now it's the derivative of the inner function, the derivative of 5x cubed minus x to the 4th. All right, so let's do that. So the derivative of 5x cubed is 15x squared, and the derivative of x to the 4th is 4x cubed, like that. Okay? This is the derivative. Fantastic. All right, check out this new one. It's 1 over 3x minus 2. All right, so notice that this is a quotient. So we could use the quotient rule, but I think there's an easier way to do this. I don't know. Let me try it. So d dx of this expression. Now, again, this can be definitely evaluated or computed using the quotient rule, but I think this way might be easier. This is equivalent to, I'm not finding the derivative yet, but 1 over 3x minus 2 is equivalent to 3x minus 2 raised to the negative first power. So then I can use the power rule along with the chain rule, again, just like I did in the previous example. So now the derivative is going to have us use the power rule here. So negative 1 comes down, and now this is 3x minus 2 raised to the power of negative 2, because minus 1 is negative 2. And then it's times the derivative of your inner function, which is just 3. So then this can be rewritten as negative 3 in the numerator, right? That's from this 3 times this negative 1. This 3x minus 2 is being raised to a negative exponent, so that can be rewritten in the denominator with a positive exponent of 2. I think I like this a lot better than using the quotient rule, but it's kind of cool that we have more than one way to find the derivative. All right, cool. All right, let's look at another one. We have sine to the 5th power of x, which is basically sine of x to the 5th power, right? All right, so here we go. So we're going to do d dx, right, of sine of x to the fifth power. Okay, so this is definitely the chain rule. The outer function would be x to the fifth power. The inner function would be sine of x. Okay? All right, so here we go. So then, let's see. So the power comes down. Oops. All right, there we go. The power comes down. And now this is sine of x raised to the power of 5 minus 1, which is 4. So now this is just sine of x to the fourth power, times the derivative of the inner function. And the inner function is just sine x, right? And the derivative of sine of x is cosine of x. All right, there it is. That's it. That's the derivative. All right, cool. A brand new example. Show that the slope of every line tangent to this curve is positive. Okay, folks, we know that the slope of a line tangent to this curve means the derivative of this function. So we must find the derivative. When we find the derivative, they basically want us to show that the derivative is going to be positive for every single input. So let's first find the derivative, right? So let's do it now. So we're finding dy dx, the derivative of y with respect to x. All right, it will be the derivative of this expression. You know what? And let's rewrite our expression. You know how it's 1 over 1 minus 2x cubed? That can be rewritten, I think conveniently, as 1 minus 2x to the power of negative 3 instead of positive 3. All right, cool. So let's do it. So this is definitely the chain rule. The chain rule with the outer function being x to the power of negative 3 and the inner function being 1 minus 2x. All right, so the power rule says to bring down the negative 3, and now 1 minus 2x is being raised to the power of negative 4 because it's negative 3 minus 1, which is negative 4, times the derivative of 1 minus 2x, which is just negative 2. All right, cool. Let's rewrite this. So this is positive 6 in the numerator, all over 1 minus 2x in the denominator, now being raised to the power of positive 4. Now, this is the derivative, folks. Now, whatever point you plug in, at any point along the curve that you consider, this expression is positive because the numerator is a positive number. It's fixed at a positive number. And the denominator, no matter what you plug in for x, when you raise this denominator to the fourth power, you get something positive. So this quotient, which represents the derivative, which represents the slope of any tangent line to the curve, is a quotient of two positive numbers. So this quotient, which is the derivative, which describes the slope of every line tangent to the curve, is positive. That was a pretty cool example. I hope you enjoyed it.